Chapter 7 is Systems of Equations and Inequalities. And for this first section, we're going to look at linear and nonlinear systems of equations. A system of equations is when you have more than one variable and more than one equation. So today we'll look at systems that have two equations with two unknowns and solve them using substitution. So, here is an example of a system. It has two equations and two unknowns. And when you are done solving a system, you have an x value and a y value. So you'll have, you'll have to solve for both. So here is the method. I'm going to talk through it as we go through our first example. So here's an example of a system. First equation, second equation, and we'll go ahead and solve using substitution. There are multiple methods of solving a problem like this, and so the first one for this section is going to focus on substitution. So the first thing you want to do is solve one of the equations for one of the unknowns. So I'm going to call this top equation, equation number 1, and I'm going to call the bottom equation, equation number 2. So when I talk about equation number 1, I'll label it. And what I'm going to do is take equation number 1 and solve for one of the variables. I'm going to solve for x. So I will subtract y to the other side. Once you have one of the variables alone, you have the x alone, you're going to take what it equals and plug it into the other equation for x. So the second equation, I'm going to write it all the way through, but instead of writing x, I'm going to write what x equals, which is 4 minus y, and then minus y minus 2. So again, I'm writing this whole equation, but instead of writing x, I'm writing what x equals. Now I have this new equation, and all it has is y's in it. It doesn't have x's and y's, so you are able to solve for y. First thing I'm going to do is combine like terms. I can combine my y's. I don't need to write the parentheses anymore because there's no coefficient and there's no exponent. So I don't need those. Negative y minus y would be negative 2y, and then I'll continue solving for y. First I'll subtract 4 from both sides, and then I'll divide both sides by negative 2. So I got y equals 1. Now I already said that you do need to solve for x and y, and so here I have one y value and I need to get my x value. I'm going to go ahead and look back at this first thing I did, and I have this equation x equals 4 minus y, so I'm going to plug in 1 for y there. You're actually able to plug it into original equation number 1, original equation number 2, or your new equation number 1, which is after you rearranged it. Any of them will give you the same answer. So x equals 4 minus y, y is 1, so x equals 3. How I like these answers written is in an ordered pair. An ordered pair is x, comma, y, so it's 3, comma, 1. That would be my answer for example 1. In these slideshows, I will have my work and kind of talk you through it, and then I also left the official, the author of the textbook, he kind of wrote through and explained how to do it typing instead of writing. And so I also left that slide in. So if you want to see, how the textbook kind of explains it and types it out, you can read through that as well. The only thing that I haven't done yet is check the answer. So, here's the answer that we got, 3-1. And if you want to check, you would sub that answer 3-1 into both equations. So here it's typed out. I'm going to do it. So equation number 1 is x plus y equals 4. It's equation number 1. And I would plug in x is 3 and y is 1. And then the question is, does that work? Yes, that works. So far, this solution looks like it will work. The second part of checking is to sub it into equation number 2. So here's equation number 2, x minus y equals 2. So I'll take my x, which was 3, and my y, which was 1, plug them in for x and y, and then is that true? Yes, it is. Well, if you can plug your answer into both equations and they're both yeses, then it for sure works. So it's a way for you to check your work and make sure your solution actually works in both equations. All right, nonlinear system of equations is when one of your equations maybe has an exponent of 2 in one of the variables. Here's an example. We have 3x squared, which means this is a quadratic equation. That means that it will be a parabola on a graph. And so, we don't have the graph of this, but what could happen is you have a parabola and then this is a straight line. So there's a possibility of having two solutions. I graphed it so you could visually see, if we're solving by substitution, but if you were to graph these, the answer is where they intersect. So that's why I did that. So we'll solve this one by substitution as well. And we'll get started. You're looking to either solve the first equation, number 1, for x or for y. Solving for x would be challenging. Solving for y would be pretty easy. Solving equation number 2 for x or y. Solving for x would be kind of a pain because you'd have to divide by 2. Solving for y would be pretty easy. So my plan is going to be, I'm going to take equation number 2 and I'm going to solve for y. I think that'd be the easiest. So first step is take equation number 2 and solve for y. I am going to subtract 2x from both sides. And then I'm going to divide everything by -1, which changes all the signs. So once you get one of your variables alone, I'm going to take it and I'm going to go into the other equation, plug in what y equals in for y. So this stuff is going to go in equation number 1 for y. So 3x squared plus 4x minus what y equals, which is 1 plus 2x, equals 7. Now in the last example, I didn't need the parentheses because there was no coefficient, there was no exponent. Here I do have a reason for the parentheses, so I'll have to distribute that minus. So let's do that. 3x squared plus 4x minus 1 minus 2x equals 7. Now I'm going to reevaluate. I'm going to look at the equation that I have. This is the result of substitution. It's what I wanted, which is only one variable. I only have x's here. It's going to be a little tougher to solve than the last one. The last one, it was a linear equation. The biggest exponent was 1 on any of the x's. Here, the biggest exponent is 2, so it's quadratic. So I need to know how to solve a quadratic equation. I can solve with factoring. I can solve with the quadratic formula. Just depends on how this shakes out. I'm going to try to solve by factoring and see if it works. So I'm going to combine like terms. 3x squared, 4x minus 2x would be plus 2x. Subtract 7 from both sides, minus 8. So when you factor, you get everything on one side, and then set it equal to 0 and try to solve it. I'm going to try just my traditional factoring and see if I can get it to work. 3x and x will be my first terms. I'll try 4 and 2, and I think those will work. I want it to be a positive 6x. I want it to be a negative 4x. And if I FOIL that in my head, it looks like that works. So I got my factoring done. I'll set each factor equal to 0 and solve. It looks like my answers are going to be, I don't like this little print down here. This one would be x equals 4/3, and this would be x equals -2. So with a non-linear equation for equation number 1, like I said, it could lead to more than one solution, and in this case, it is leading to 2. I have this x value and this x value, and both of those x values need their own y values. So I'm going to go back to equation number 2, my edited version of it, where I solve for y, and I'm going to plug each of these x's in for x right there and get my y. You can plug it into equation 1, equation 2, or the edited version of either of those, and it works. So now I'll find y. Y equals 1 plus 4/3. Oops, I forgot that too. 2 times 4/3. To figure out what that is 8/3. 1 is 3/3 plus 8/3, so it looks like that's 11/3. And then if I plug in -2, I'll get 1 plus 2 times -2, which would be -3. So my first point was x was 4/3 and y is 11/3. My second point is x is -2 and y is -3. Those are my two solutions. I would want to check both of those and make sure they work. I'm going to do that. Let's see, I'll do that up here because I'm kind of running out of room. So checking, I'll first check 4/3 and 11/3. So I'll plug in x is 4/3, so I have 3 times 4/3 squared plus 4 times 4/3 minus 11/3, and then we'll see if that equals 7. Here this would be 3 times 16/9, and that is 16/3, plus here this is also 16/3 minus 11/3. 16 plus 16 is 32. 32 minus 11, that's 21/3. And does that equal 7? Yes, it does. So that first pair worked in the first equation. Now we'll check it in the second equation. So equation number 2. 2 times 4/3 minus y is 11/3. Does that equal -1? Well, that's 8/3 minus 11/3. 8 minus 11, that'd be -3/3 equals -1. Yes, that also works. So again, I'm taking x and y, plugging them in for x and y in equation number 1, checking to see if it holds true. If I didn't make any mistakes as I was solving, it should be fine. I'm just checking to see if they work. If they wouldn't work, that means I made a mistake earlier and I'd have to re-solve the problem. All right, so that was the first one, the first point. Now I got to check my second point. Should be easier because it's not a fraction. All right, so equation or point number 2, -2, -3. I have to plug it into both. So check number 1, 3 times 4/3 squared. Oops, no, I'm doing the second point. -2 squared plus 4 times -2 minus -3 equals 7. -2 squared is 4. 4 times 3 is 12. 12 minus 8 plus 3 is 7. So that's a big yes. Now I'll check equation number 2. 2 times -2 minus -3. Is that -1? -4 plus 3. Yes. So both of these are good to go. Checked them both equations, good to go. All right, and again, I said I left, you'll see in all my videos and all the slideshows, I'll leave the typed solution. So if you prefer to look through and read through that later, you can do that. It is just the typed out version of my solution. I just wrote it out as I talked you through it. All right, so we've done all that. The graphical method for finding solutions is also in this section. We talked about solving by substitution. Graphing would be if you graphed both equations and the solution is going to be the points of intersection. So there might be 1 point, 2 points, more than that, 0. There could be any number of solutions. So I did here, I left the graph here that they have. Here's a system y equals ln of x. That is a logarithmic function. We're going to get to that later on in the course. Here it is. Here's a graph of it. I'll highlight it. And then the second equation is just linear, and it is here. So if you were to graph these, you could graph them on a graphing calculator. You could graph them on Desmos. What you're looking for is the point of intersection, and it's where they cross, and here it crosses at 1, 0. So that is my solution. Here's the checking. You plug the x equals 1 in for x, you plug 0 in for y, and you check them both, and you make sure that it works. One of the applications that will recur in this course over and over is break-even point. And so we'll talk about that right away here. It says when enough units have been sold so that the total revenue equals the total cost C, the sales are said to have reached the break-even point. So this is a business application. Applications are like word problems when we're studying math. You know, we want to know where would this math be used in, you know, the world, in either a business field, maybe a science field. You know, just depends on who uses this content in their, you know, their life and problem solving at their job. And so here, this is a business example. It would be a break-even point. It's where you are taking in enough money so that it's covering all your costs. You're not making a profit, you're not losing money, you're just breaking even. Graphically, the break-even point corresponds to the point of intersection. So if you're looking for the break-even point, you are looking for the intersection point. So what we'll do here is we will write an equation that represents the total cost. Then we'll write an equation that represents the total revenue. And then we'll set them equal. So this says a shoe company invests $300,000 in equipment to produce a new line of athletic footwear. Each pair of shoes costs $15 to produce and sells for $70. So we're looking for the cost. So we want to know how much it costs to produce. It's $15. We'll say the number of units is X and the initial cost is $300,000. So this is going to be what I call C of X, or even just C. But this is going to be my cost equation. Depending on the number of units, this is what it costs to produce them. Here it is typed out. Now the revenue. Revenue is, you know, money in, so we'll call it R, or R of X. Price per unit, I think it was $70. Yep, sells for 70. So every time you sell one, you get $70. That's the only way you make money, is selling them. So this is equation number 2. And this is wrong. This should be R. So the break-even point here, it says that the break-even point occurs when R equals C, revenue equals cost. So I have revenue is 70X and cost is 15X plus 300,000. So what I'm going to do in order to solve it is I'm going to set them equal to each other. I'm going to say 15X plus 300,000, that's my cost, equals 70X, my revenue. So this is for break even. You set your cost equation equal to your revenue equation and then solve. First, I'll subtract 15X from both sides. So I have 300,000 equals 55X. Then I'll divide both sides by 55. So my X, or my number of units needed to be sold to break even, is 5,455 units, and then we will break even. If you sell more than that, you'll make a profit. If you sell less than that, you will lose money. Here's the typed out solution. And then here's a graph of it, which I think is kind of nice to look at. So here is our revenue equation. This is money in. Cost equation is here. This is money out. And then in the middle, you have your intersection point, which is your break-even point. So you can see, you know, as you go past on the x-axis, as you go past 5,455 units, as you go past that, you will make a profit. And if you don't sell that much, you will lose money.